Hello everyone, and welcome back to another remote sensing lecture video. And in this lecture video, I want to go through another set of examples um, detailing that idea of contrast stretching. And in this case, I want to work with data generated from a different image that has a different bit depth, so you can hopefully see a different approach, a different perspective, I guess, um, on this idea of contrast stretching, so you don't get bogged down in just the Landsat example. So what I want to do before we do anything else is I want to show you our image histogram. And I want to talk about the theoretical minimum, maximum, actual min, actual max, average, and median. You may remember this is the exact same image histogram that we talked about in the image histogram video, but I just want to quickly recap it here. That we have a theoretical maximum of just over 2,000, whereas our actual maximum is sitting right around here at just over 1,700. Our minimum is obviously 0. We do have some pixels, again, only 94, that have a value of 1. And this value, the 1,700 pixel, is only 1 pixel. So this is what I was saying before about how the min-max contrast stretching can be really affected by these weird outlying pixels. This is exactly why, right? Our actual maximum has only 1 pixel. And our mean is 300. So our mean is way down here, right? The majority of our pixel values are way over here. We have 1 pixel way out here that's going to mess up all of our histograms. So let's go ahead and let's go through the first example again. What happens if we do nothing? All right, well, if we do nothing, right, or a non-histogram stretch, what it does is it takes the theoretical maximum, so this is the maximum based on the radiometric resolution. It sets that equal to 255, right? So that's what this is saying. And it's going to make that bright white. So in this case, I've tried to sort of show you roughly what colors they would have. The theoretical minimum of the data becomes 0. So in this case, 0 becomes 0. And then everything else, right? All these other things are linearly interpolated based on those values. So because 1 is so close to 0 and going from just over 2,000 pixel values down to 255 display values, right? You're going to have to combine things. So in this case, we're already seeing that. The actual minimum of the data becomes 0. The maximum, the actual maximum, so this is the first pixel value that is actually used, right? It becomes 215. So that's what this line is representing here. Then the average of the data becomes 41, and that's what this line right here is representing. Okay, so that's what happens if we do nothing. You'll see that the vast majority of pixels have values less than 20, have display values less than 20, and almost all of the pixel values have display values of less than 100. So now I want to look at what that would look like in an image. Overall, the image is pretty dark in general, right? And again, that's because you have to consider the fact that the middle value, right, the middle display value would be roughly 125, right? Almost every single pixel is well below that halfway mark. So hopefully that explains why this image is so dark. So I want to look at 3 specific pixels here, and I'm going to track these 3 pixels as we go along. Again, these are approximately what color they would look like in the image. So this one, here, here, and here. So let's talk about what we can do with min-max. So again, min-max takes the actual minimum of the data. Min-max takes the actual min of the data and sets it to 0. So by default, the theoretical min stays 0. It now sets the actual maximum to be 255. The theoretical maximum, again, becomes 0. And so you can see here that the contrast stretching, right, now we've got more values sort of creeping up. It's still not perfect because we had that one outlying pixel with a very high pixel value. But you can see that we're starting to sort of creep the hump here. It's starting to creep towards more moderate pixel values, or sorry, more moderate display values, which is exactly what you want, right? You want the bulk of your pixels to be in the middle of your display values so that we have a really good contrast, which is why this is called contrast stretching, because you want to be able to see the differences. So let's see what this looks like in terms of an image. Right. Now you may not think that this looks much different than the non-option that we did before, but as we go through the comparisons, you'll see that it actually did improve it at least a little bit. So again, these are those 3 pixels that we're concentrating on. So this is them side by side. And again, hopefully you can see this might actually, in this particular instance, it may be based on the color properties of your monitor, but hopefully you can see that this is a little bit lighter and that for each one of these comparison pixels, they're a little bit lighter. Because again, we've gotten rid of those unused pixel values, especially at the top. Okay. So what about percent clip? So percent clip, again, you're getting rid of the lowest portion and the highest portion of the data that we would assume would be erroneous pixels, right? That one pixel that had the potential maximum, right? We don't want that anymore, right? We're saying that's too much. We're going to cut out some data. And you can see here that this has had a huge impact on our distribution, right? Ignoring the top 5% of pixels or 2% of pixels or whatever percentage we chose, right? It bumped that theoretical maximum to 255, and then it jumped all the way back down a ways, right? This is now what? Almost 775-ish, right? This is the top 5%. So this became 255. Everything above that also became 255. But you can see what that's done here, right? Now, I'm going to go back a couple slides, right? The majority of our pixel values still had display values below that sort of middle of 125. But if we jump down again, right now, look at that. We've managed to spread our pixel values out across the full range of display values. So what does that look like for the image? Now, hopefully you can see that the landmass has gotten a lot brighter. And that's because we've ignored some really bright pixels that were in here that may have been errors, right? So we made the landmass a lot brighter. And we've made some parts of the water where you have some runoff or some sediment, right? Those are starting to pop up now as well. So let's look at our 3 pixels. Now this one is very bright. This one's medium gray, and this one's now still really dark. But let's compare that to what happens if we hadn't done anything. Now you can really start to see that difference. Right on the left, things are still really dark, and on the right, the landmass especially has started to brighten up quite a bit. And again, that's because we're ignoring those really high values and those really low values. We're assuming those are erroneous pixels. We don't want them to mess up our contrast, so we're going to just exclude those, and we're going to jump into the meat of the data and stretch that across the display values. So finally, let's talk about standard deviation. So standard deviation is going to look very similar, especially in this case. But again, the difference is with standard deviation, you're starting in the middle and you're working out, whereas with percent clip, you're starting at the ends and you're working in. So hopefully that makes sense. So you can see we have kind of roughly the same thing, but we've actually shifted the water pixels, right? These dark pixels are starting to shift up a little bit. Let's see how that looks. All right, again, this looks very similar to percent clip. Here's the pixel values. Again, landmass is a lot brighter, and you can see the differences here. Now this is side-by-side percent clip and standard deviation. And the reason I wanted to show you this is a good example of how they're different. So in this particular case, percent clip is actually a little bit brighter than standard deviation, but usually standard deviation will be brighter. The reason this is this way is because there's so much water in this image that we have so many pixel values devoted to this dark water, that it actually makes percent clip a little bit brighter. But normally standard deviation would produce the brighter image. So hopefully this made sense. I know I walked through this a little fast. I'm hoping that you already watched the previous example and this was sort of another view on it. If you haven't, I would encourage you to go back and watch that one. If any of this doesn't make sense, please reach out. Thank you.